what we're going to be doing, obviously now you've run this, but we're going to talk through this notebook, and I'm also going to talk a little bit about why we're doing this comparison. So, as many of you know, Mauna Loa is the world's biggest volcano, and it erupted in 2022, but after a long period of repose. And as a result of that repose, it hadn't really been nearly as well studied as nearby Kilauea. One of the original papers looking at magma storage conditions at Mauna Loa had noted the presence of orthopyroxenes with high magnesium numbers, about 86. That's really unusual for Hawaii. You do not see those orthopyroxenes at Kilauea. And they actually use P-melts to look at phase stability, so basically make a phase diagram for a Mauna Loa primary melt. And they showed that you could only get those high magnesium number orthopyroxenes at greater than about 6 kilobars pressure. Now, that led to this whole thing in Mauna Loa petrology, where suddenly there was this suggestion that there was this shallow reservoir, which has been imaged by geodetics at about 3 to 5 kilometers, and that then there was this deeper reservoir below the moho, which must be required to stabilize these orthopyroxenes. It was then shown experimentally that if you put these orthopyroxenes into their carrier melt, they dissolve really, really, really quickly at 1 atmosphere pressure. That's how the experiments were done. So there was this model where melts were bringing up these orthopyroxenes from below the moho in 24 hours. And that is pretty concerning from a hazard perspective. So we started doing melt and fluid inclusions on these orthopyroxenes. Alex and Heather Winslow on this call have also made those measurements. And we did not see these really deep pressures, nothing like 6 kilobars. Obviously, if you had followed Paul's workflow, you would think P-melts is a bit of a weird thing to do. This is not the mantle. In the original paper in 2002, they did say that Mark Giorso had said that it was fine to use P-melts for this circumstance. So we basically wanted to see, by running phase diagrams, do all of the models agree that you can only stabilize orthopyroxene at these high pressures, or is there disagreement between the models? So as normal, the first cell is just loading your melt stuff. You should all be aware of this by now. Suppressing your outputs for Mac. And then the key thing here is we have to specify a bulk composition. Choosing a bulk composition for a primitive liquid is obviously quite difficult. This is particularly difficult at Mauna Loa, where there are basically no highly MgO liquids erupted anywhere on the edifice. So to start with, to do these kind of calculations of what is your initial thing coming into the system, you would have to run a reverse fraction of crystallization path. I actually ran this in Petrolog because that's actually a lot easier to do it in, but I think Matt is planning on making it easier in PetThermoTools. So basically ran from a measured liquid composition back to 20 weight percent MgO. Also did some calculations for 16 weight percent MgO in the paper, as there's disagreement as to the primary MgO content of Hawaiian magmas. And that is going to be our primary melt composition that we're going to be running these phase diagram calculations from. So Matt's talked a little bit about this, but just in terms of what this calculation is actually doing, to start with, if we set up a grid of, say, 16 points, it is basically doing an equilibrate calculation discretely at each of these points. It is not truly continuously searching across PT space. And then what the algorithm is saying, if you've selected that refinement step, is it's saying, okay, well, we've got two calculations that both return olivine and liquid. So we're assuming that the thing in between that is also olivine liquid. Now that can be a problem. If you have set too large a delta T and a delta P, you might actually miss a thin slither. So you can imagine there could be a slither of like CPX stability coming in here that you would miss. But if you've set a reasonable spacing, chances are you probably haven't missed that, or you would catch it further down where the wedge reappears. But basically, so it's saying in between these 2 points, there's a change in phase. So there's liquid on one side and olivine and liquid on the other side, sorry. So what the algorithm does is every time you have a difference between 2 points, it is adding all of these red calculations. So that would be refinement step 1. It then does the equilibrate calculations at these red pixels, and then it decides, this one was olivine liquid, this one was olivine liquid, this one was liquid only. So that would be refine 1, and then it's basically filled in all of these little circles are just ones that's extrapolated because it doesn't need to redo that calculation. It's assuming if it's that on one side, it's the same on the other side of it. Refinement step 2, you can imagine would do the same thing again. So you'd insert more of these red dots. And what it's going to basically do is the more refinement steps you set, obviously the longer the phase diagram is going to take, but it's going to mean your phase boundaries go from being big stair steps to eventually being nice lines, depending on how much computation you can afford to do here. So for the first one, we are naming this variable res pmelts. This is our results from pmelts. We're using the pmelts algorithm. We're setting the bulk composition to that primary melt above. And on my laptop, I can just about handle 25 pressure steps. So from 200 bars to 1500 bars. And then equally 25 temperature steps from 1150 degrees Celsius to 1450. I'm then refining this twice. So that would do this whole step twice, basically. Okay, and this is what the output looks like. So you can see it's not a dictionary like some of our outputs. This one is just a data frame. And it basically has the T and the P and then all of the thermodynamic properties. And then if you were to look at the columns for this, which you can do with dot columns, let's look at the first 100. You can see you've got things like the magnesium content in the olivine, the magnesium content in the liquid, the magnesium content in the orthopyroxene, etc. So that's everything that you would need. We then can use this built-in function, ptt.plot phase diagram, and you simply give it the name of that data frame that it's made, and it will output this. So again, the only reason you need the interactive plots, and if they're being a pain in the butt, don't worry about it, is say you weren't sure what this number said, say there was like way too many phase fields on top of one another, you can hover over this and it will tell you at 1153.4 degrees Celsius and 1550 bars, you have 11, and you can come over here and see that 11 is liquid, olivine, spinel, and plagioclase. So that's the only need for the interactive plot, otherwise you can deal with this as is. What we then do is we run this with melt 1.0.2, and you will see, it's exactly the same inputs other than the model. This is having some more failures. So you'll notice that this attempt 0, this basically means that P-melt's like, Matt or maybe when Matt's back can explain exactly the failures that are happening and when. You'll see in a minute when there's some holes. Basically, this just tells you it's going through and it's reallocating calculations after some of them fail. And then we're going to do the same for this green one. This is slower. Again, all phase diagrams are slow. This is like a lot of points that you're calculating, so they're never going to be like absolutely lightning speed. So generally, I tend to run them overnight or during lunch. And then what we can do is we can use this phase diagram multiplot. This actually allows us to plot the two phase diagrams with the same color scheme. And this is because it's really annoying if like black in one output is liquid and black in another one is liquid plus olivine. Because if by default you just run them through this code, they will not share the same colors. So the point of this function is it means that we're basically feeding it the melts one and the name we want to give it, and then the name. And this is actually, one second, that is labeled wrong. It should be 102. So this should be 1.0.2. Oh, there we go. 102. They're very, very similar, the two melts versions for this. And then green. So basically you can see that, for example, field 13 here, this is liquid olivine OPX spinel. And then the same 13 down here, we might not even have. But you can see for 3, for example, 3 is liquid olivine and OPX. And then you can see 3 is here. So this liquid olivine OPX field is actually the field that we're most interested in this example. This is your observed phase assemblage at Mauna Loa. So you can see for the melts 1.0.2, that should read. 1 second. You can see that you can get this OPX stabilizing at about 2000 bars. That's not massively inconsistent with the melt inclusions, and the fluid inclusions, which can stretch down to like a kilobar or 1000 bars. And then you can see in comparison for green, it's a little bit higher up. So what I'm going to suggest you do is try changing one of these to P-melts and then see what the P-melts stability looks like instead. So go like this. You could also, I think you can keep all of them in as well. We can do that in a second.
Yeah, if that works, if you're able to do this whilst we're waiting for everyone else, try doing all 3 phase diagrams. You should be able to do that as well. So this is just putting them as a dictionary. So the key and then the data frame, that's the output. And the key is going to be what it labels it as. And Penny, that is a horrible color map.
Yeah, so I did this on purpose. Sorry, I meant to say you can choose your color map here with this color map statement. Matt, can you paste in all the options to the Discord so people can see them? So what I hope you actually, yeah, post your results. Once you get your P Melts one and you've chosen a color map that Matt's not going to critique, paste in a screenshot of that just so we know people have caught up to here. I'll go up so you can see how I did this.
Do you want me to talk about the IMAX thing?
Yeah, do you want to talk about the IMAX thing briefly?
Yeah,
Well,
can you guys hear me okay?
yeah, I can hear you.
Um, one sec, there's one error. I'm just gonna quickly try and see. Uh, um, yeah, for Sue's one, it doesn't seem like the calculations are running correctly. I can't work out why. I will
Woohoo. Okay, so we've got some P
yeah.
Melts calculations. Um, Gustavo, I like your color map. What color map is that? I can't remember its name. Magma! Oh yeah, we got to use magma. I mean, come on, it is a Melts workshop. So I hope what we can kind of see from these results is that the P Melts, liquid Olivine OPX field, which is 5 in this case, is really offset to higher pressures relative to both Melts 1.0.2 and also green to an extent. Green extends down a lot lower. So to start with, you can say, okay, that need for sub-MoHo pressures is unique to P-melts. The fact that there isn't a lot of convergence between these models is a little bit complicated. What you'll then notice is, say you just care about that phase assemblage, it's actually a little bit awkward to try and compare these with just these phase diagrams because you can't like plot these all on top of each other. It's going to look absolutely horrible. So next, we're just going to go through some other ways you could plot this. The first thing that we're going to do is we're going to calculate the mg number of the orthopyroxene. So that's just from the oxides and their molar masses, just so that we have that again, because the original paper was tied into using the magnesium number, not the temperature and pressure. And then there's this function basically make grid variables from phase diagrams. So what you might want to plot is you might want to plot the percentage of OPX as a function of pressure temperature, as a function of pressure mg number. That is very hard to do from the data frame structure that the function has returned. So you basically want to sort it in a way that's actually like plottable in those two dimensions. And that is what this function is doing. So basically you give it your data frame and then you give it what you're going to want to plot on your x-axis and what you're going to want to plot on your y-axis. And then from there, you can basically, it will restructure into this x, y, and then the z. Matt, remind me what the z is. My brain's frazzled.
So the Z is
Oh, that is everything.
everything,
Yes,
yeah.
every single column other than the two you've specified are now arranged in this nice way. Okay, so you can access any of them. So here we're just interested in, say, we could be interested in, say, the mass of liquid, and you could then extract that from this Z column that has all of. So basically, you could plot any of these Z values. So you can see you could plot anything that is now reformatted in this nice way. So we're going to do that for each of the models. So we're going to do that for the green, the melts, and the rhyolite melts. And then, so we're setting up a subplot here with 3 axes, and we are going to use this p color mesh function. So basically here you're going to specify your x and your y coordinates, and then you're specifying what you basically want to be colored onto that. So we're going to specify the mass in grams of orthopyroxene here. Again, we can choose a color map. We can scale that color map to say we're particularly interested in the onset of OPX saturation. So we're going to say we want all of our colors to be distributed between 0 and 10 grams. And then again, you could write this in a loop for all the models, but I just explicitly wrote it out. So you've got it for the melts, the P melts, and so on. And this is a slightly easier way to visualize things, maybe. You can see this is basically the onset of OPX appearance in the models, and you can see it is occurring at significantly lower pressures in the melts. Matt, maybe now we've got these white gaps, this is a good time to talk about your that parameter.
Yeah, sure. So you'll notice that in both the melts and the P melts, you have some artifacts. Some of these are the white gaps. Some of these in the melts 1.0.2, you see the little points up there where you have the little purple areas where they clearly shouldn't be, essentially. And what you will find is that when trying to do these calculations, especially in many cases when you're going towards the kind of like the extremes in your pressure temperature space, so maybe you're going down to relatively low temperature at low pressure, or you're taking things for melts well outside its kind of like stability range. So for the melts, 1.0.2 is typically advised to be used like below 500, so 5 kilobars, 5,000 bars. If you're taking it well above that, then maybe you're well outside that kind of like calibrated or advised pressure range in that case. And basically, what will sometimes happen during this system, so we will set up a PT grid to run in a phase diagram. That PT grid will then be split into different segments, and each segment will be sent to a different process. So if you put cores equals 2, it will basically split it in half and send 2 halves to a different process. Each process is then going to run through its grid, first going down in temperature and then stepping down in pressure and running through each way. Okay. So it's kind of like going down these steps. But what will sometimes happen, and Paul kind of showed this earlier when he had the fractional crystallization example that didn't converge and didn't return results if you run it all the way down to really low temperatures. What we will do in that case is Python will hopefully identify that a calculation has failed and return the data that has been produced up until that point. Okay. So as it goes down to lower temperature, Python will return the melts calculations up until the point of failure. But it will also mark that failure point. And the other thing that's happening is if it, say you had 100 calculations to happen in that process and it failed on calculation number 70, it's going to leave 30 more calculations that it never got around to even attempting. And so what it's going to do is it's then going to go and say, okay, we're going to close all these processes, save that kind of stored data that we calculated so far, and we're going to try again with everything that's left. So for every point that's left over after the first attempt, it's going to go back and it's going to try and calculate them again. And this is basically where the Imax parameter comes in. Because in some cases, you might get into a specific field of PT space where it's very, very hard for melts to find a solution. And you just get continuously getting error after error after error. And you might just get this region where you're very unlikely to return a full solution. So in the melts 1.0.2, it looks like it might be this kind of like 1360, 1370 kind of range in here, where we seem to get in this white box. Okay. The Imax parameter is basically the number of times melts or PetThermoTools will restart the melts calculations to try to fit in that grid again. Okay. So if it tries to fit in all the points and it hits more than 15 failure points, so it fails and leaves some calculations undone, at that point it's going to say, okay, we're not going to complete this calculation. We're going to return the results up until the point that we have, fill in the empty values with either zeros or nans. I can't remember off the top of my head which one it is done. This is basically implemented so that these calculations don't just continue on forever. When I was testing this, I did run into a couple of cases where we just had like a series of failure points that just kept bouncing back off each other, and never, no matter what happened, they just never seemed to converge on a solution, and so the phase diagram never completed itself. By having this Imax parameter in there, it means that we put a limit on how many kind of iterations we're going to give it in order to try and calculate that phase diagram. The reason why I suggest keeping Imax at 15 is sometimes you'll have a calculation failure that doesn't properly get picked up by PetThermoTools, and it will retry the same point again. This is not what it's meant to do. And when I find out why this is happening, I will remove it. But it means that if you have your Imax more than 15, it will continue attempting that one point, say 25 times or 100 times. You put Imax to 100, and then that can just take a very long amount of time whilst you're waiting for this to complete that process 100 times, essentially. So it's worth, yeah, it's worth keeping the Imax at 15 The only thing you might find is that if you set your initial grid size to like 100 by 100 or 200 by 200, you might find that with IMAX of 15 for some of the melts calculations, if it hits enough failures, you might just find an entire region of your phase diagram has not been calculated. And that's because it ran out of iterations in order to repeat itself. So that's kind of what the IMAX is doing. Every time it's hitting one of these points where there's a white space, it's hitting a failure, it's stopping the calculations, working out what's left to calculate, redistributing those to the Python processes, and then trying again. And it's going to do that a maximum of 15 times. And I think in these calculations, Penny, if you scroll up, it does that for melt 1.0.2.
Yeah, which is the one that's leaving all the horrible big holes if we
Yeah.
go. Yeah, so you can
So,
see.
and this is happening so that it's printing 3 times because we have 2 refined steps. So the first 0 to 15 is the first attempt at doing a phase diagram. And then the second 0 to 15 is the first refined step where we're fitting in those kind of the areas where there's a change in the phase assemblage. And the same for that third set of 0 to 15. That's the second attempt when we're kind of fitting in change in the phase assemblage.
Cool. Thanks, Matt. So again, this is still, it's a little bit easier to visualize, but it's still not great. So another thing that we're going to do is we're going to set up some of our true false statements. So now we are going to make a data frame which is only got the rows where the mass in grams of olivine is greater than 0 and the mass of grams of OPX is greater than 0. And we're going to do another one where we just say the mass in grams of OPX is greater than 0. And we're going to do that for green, for P melts, and for the rhyolite melts. And then we're going to come down and we're going to plot those smaller data frames again on a subplot situation. So again, we're plotting temperature versus pressure. But here we're only plotting the places where on the left-hand side, olivine and OPX is stable. So here you can really start to see that the green extends to about 2,000 bars less than the P melts, and then the rhyolite melts extends to much, much, much lower pressures. You see that for the olivine OPX stability field, and you also see that for the OPX stability field. So there's various ways to visualize this. What I honestly have to admit I did in the final paper is because it's still hard to see these things. I then imported this into Illustrator and drew around the area on top. You can try and get Python to do it for you. The fact there are a few artifacts, you can kind of see them floating around here, just meant it was easier to just draw on top of it by hand at the end, I have to admit. But that gets you most of the way there. We could also make the plot in mg number space. So here we've just swapped out that temperature for mg number of OPX. And this, again, you can really see that at mg number 86, which is the point at which the Gaffney paper said they were at and they were worried about the formation of, you could stabilize that at 3.4 kilobars in green, but you would have to go up to 6 kilobars in P melts. So just one final plot. Again, I'm not going to go into this in too much detail because I want to have a little bit of time to talk about like what you do once you get this massive amount of model discrepancy. We could just plot this yet another way. So here I'm just plotting the region where olivine and OPX is stable for each model on the left-hand side, and the region where just OPX is stable on the right-hand side. And again, this is kind of where often you need to go and just like these points are very likely not real, wouldn't you agree, Matt? So the like,
Yeah, if you're seeing
yeah,
those furious ones, I would question
you
if
see a few bizarre things that
you
you might
might
want to
even
just.
find occasionally like that some of these might have like the weird cyanopyroxene 3 or something. That like if you look at the composition, it might be some of those very weird outliers, or weird orthoprotein, sorry, in this case. But yeah.
So, say you've done this, say you really care about your phase diagrams, you want to use them to, estimate magma storage, and you're presented with this. And we added some other models on in the paper. We did some petrolog calculations, we did the other melts, we did the other Holland and Powell models as well. And there is just a huge amount of variety. So, how do you know which one to trust? So, what we decided to do is Paula has, what's the best way to access LEPR right now, Paula? Do you want to post it in the Discord?
Okay, so this it's a development site at the moment. It's not all right, hang on.
I can give you a minute to find a link or
Yeah,
something. I can just so
yeah.
basically the LEPA, for those who don't know, is the Library of Experimental Phase Relationships. It has a lot of experiments compiled. So what you can do is because I'm obviously here particularly interested in orthopyroxene stability, I grabbed every experiment which stabilizes orthopyroxene. And I've just plotted them up on the left-hand side here in silica magnesium space. And what I've decided is like, not all of these are relevant to Mauna Loa primary liquids. So I want to filter that data set for those which are. So what I'm just showing here is these are Mauna Loa matrix glasses, and then this is two different fractional crystallization trends, one which is olivine only, one which is olivine and then OPX coming in at certain points. And then basically just chose experiments which lie somewhere near this line and said, okay, they're my experiments that I'm going to use to validate how these models are doing. Plotting those in PT space, you immediately see a problem. You see there are an awful lot of experiments done at 1 atmosphere. That is this strong line down here. And then you have this step up. You've
Penny,
off.
Penny, I don't think we're seeing what you're seeing. We're still
Oh
looking at the
no!
olivine OPX
No!
stable.
Okay, we'll try this
Sorry.
again. Oh no. Okay. Thank you for
I was
buzzing
trying to
it.
solve a bug and I just realized. Sorry,
Do you
my bad.
see it now,
Yes, we see
everyone?
it now.
Okay,
Yes.
so here's my silica magnesium trend. You can see these are the experiments I've decided are compositionally relevant for Mauna Loa. I'm plotting them in PT space. And what I'm showing here in gray is these are the pressure temperature constraints from fluid inclusions and olivine compositions. Right away, we have a problem in that there are very, very few experiments done at relevant conditions. There's been a lot done at 10 kilobars once you get up to your piston cylinder, a lot done at 1 atmosphere, not a lot done in between. So it's not a great data set, but we can start to ask questions of, okay, well, what model is performing best for this data set? So we did that in a variety of ways in this paper. And again, all of the code is on GitHub, so I can share it. So the first thing that we did is we just simply said to each model, so to PMALS 1.2.0, 1.0.2, Holland, Weller, and Green, these are all different versions of the MAGE-MIN model. Holland was the original one. Weller is that anhydrous one, and Green had some tweaks to the orthopyroxene model from the Holland. So basically, use the equilibrate function. You know the experimental temperature, pressure, bulk composition, water content, oxygen fugacity, and ask these models, equilibrate this system. Do you stabilize orthopyroxene? Obviously, the answer should be yes. If there's orthopyroxene in the experiment, it hopefully does stabilize it. What you can see is each one of these dots, I basically binned the experiments into different pressure bins, is saying like how many were actually stabilized. So you can see at 0 to 0.5 kilobars, that's mostly your 1 atmosphere experiments. Rhyolite Melts 1.2.0 actually did pretty well for about 75% of the experiments that had orthopyroxene. It said, yes, you have orthopyroxene, which is the right answer. In contrast, what you'll see is P-Melts for those experiments, even though they all had orthopyroxene, it didn't say that a single one of them stabilized orthopyroxene. And you can see that the Holland models lie somewhere in between the two. Now, once you get to higher pressures, the point at which you're supposed to be using PMELTs, you can see that PMELTs did start to do better. Although I will say the number of experiments is shown at the top is extremely small. And this just shows, a lack of experimental constraints. We need more experiments. But actually, overall, when we look at it, we see that really none of the models are being super successful. That Holland model has the most overall success, largely because it's doing very well in this 9 to 10 kilobar bin, where there's actually a lot of experiments. So this is to answer that question of like, do you trust the major elements? Can you use melts to say where magma storage is at your volcano? I would do something like this. And based on this model performance, I wouldn't be super comfortable trusting the results down here, because I'm getting massively different results from every model, and also because no model is really standing out as being extraordinary in this range. Just some other things you can do is here we're plotting the experimental mg number versus the calculated mg number in the thermodynamic model. You can see that actually where PMELT does predict OPX stability, it's doing a very good job, and that's likely because it's getting that temperature right. Melts has got that offset because that temperature is offset from reality to an extent, and then you can see the Holland models are really very, very scattered in their mg numbers. So again, this really just reflects that like the region of PT space we're working in. Here on the left-hand side, we're showing experiments with OPX that were OPX bearing, and on the right hand side we're showing all experiments that have ever been put into LEPR. There's basically just no experimental constraints in this region that we're working on, so it's kind of unreasonable to expect, you know, these models to do super well when there aren't any experiments. So I think for that, what we'll get you to do is practice playing around a little bit more with these phase diagram outputs. So what I would like you to try and do now is make a plot that shows pressure, temperature, but you're going to try and color it by like looking at how the four-strike content of the olivine is changing in PT space from these phase diagrams. So have a go and see if you can do that, and we can answer any questions. So remember, you can make you might have to do things like calculating the four-strike content of the olivine because that is not returned, and then you will be able to extract that from this Z parameter once you've got it. So have a go, and we'll see how people get on, and then we'll loop back in about 5 or 10 minutes.